All right, hi guys. We're going to start a little bit of stoichiometry today. So let me get my screen shared with you, and let me go to our PowerPoint. And I would suggest kind of writing some things down kind of as you go here. I'm going to try to write using my iPad. I'm going to write on the presentation if I can get to it. Here we go. All right, so today we're going to talk about stoichiometry. Don't worry, I won't make you spell it. Stoichiometry has to do with changing from one quantity, such as grams, to a different quantity in a balanced chemical equation. So the idea here is if I start with a certain amount of grams of one substance, I can actually do a calculation, math calculation, to figure out how many grams of a product I will actually be able to make, okay? So just a quick review here on the mole. We kind of already covered a little bit of this. Just a reminder that mole is the number of particles contained in a sample of an element or compound with a mass in grams equal to the atomic or molecular weight. Remember, the mole is a counting number. So we can say a mole is 6.022 times 10 to the 23rd atoms or molecules, depending on the smallest piece of our substance. Sometimes called Avogadro's number. And when we converted from atoms or particles to moles, we use this equation or the conversion factor on the left. But if we wanted to go, excuse me, from moles to atoms, we flipped it and we put that 6.022 number on the top, okay? We're not going to do a lot of converting with atoms and molecules here. We're going to more focus on mass. So the idea here at the top is that 1 mole is equal to a certain amount of grams. That's really where we're going to spend our time, okay? So you look at a chemical equation. Remember, the left side are reactants, what you're starting with. So N2 and H2 are our reactants. The right side is our products. That's what we're ending up with. Now, the coefficients or the numbers in front, we can interpret that in two ways. We can say at the particle level, 1 molecule of N2 reacts with 3 molecules of H2. And in that process of those atoms sort of breaking apart, rearranging, it's going to make 2 molecules of NH3. Or if you really scale up, those coefficients in front also tell you the mole ratio. We would say for every mole of N2, we need 3 moles of H2. And in process, we can make 2 moles of NH3. Okay, so those numbers, the 1, the 3, the 2, those are going to be really, really important. Those are going to be our numbers that we're going to use to do mole ratios to be able to convert or change substances. The coefficients are the numbers in front. The subscripts, those are the low numbers, like N2, the 2 there, that is a subscript. That's not the same thing as the coefficient. The coefficient, the 3, the 2, and then this is kind of an implied or understood 1 in front of N2, okay? Sometimes you'll see in some of the problems in excess, what that means is we have more than enough of that particular reactant. So we're focused on the one that is a limited amount. And we'll get into later in this unit or chapter, we'll get into limiting reactant problems. But in case you see that term in excess, it means we have plenty of it, okay? All right. Whoop. Need to know 2 main ratios when we do stoichiometry problems. First of all, knowing mole ratio. So being able to use the coefficients to know that 1 mole of this and 3 moles of that makes 2 moles of product. That's important. And we're going to use those mole ratios as conversion factors like we did before. But the other ratio that we need to know is molar mass. Remember, 1 mole of a substance is always equal to a certain amount, excuse me, of grams from the periodic table. So you will have to do a little bit of molar mass calculations as we kind of do some problems here. Okay, I'm going to show you a diagram that I think does a pretty good job of understanding and explaining overall what we're trying to do here. And I'm going to write a couple of things on this diagram. First of all, if you are, this says given quantity. So let's say this is a certain amount of grams of A being a particular substance. And we're trying to go to quantity of the unknown. Let's say we wanted to convert that to grams of B, okay? What you can't do is you cannot go directly from grams of A to grams of B. Okay. The process is you have to go through the mole to get there. So this little diagram here kind of shows you that the first step of the process is to convert to moles. So we go underground, convert it to moles. So we would convert from grams of A to moles of A. That would be our first step in the process. How do we do that? Well, we would use molar mass, right? Because we know 1 mole of A equals a certain number of grams of A, right? We would use that as a conversion factor. And then the second step of the process, so that's step 1. The second step of the process is to move from moles of the given A to a different substance, moles of unknown, we're going to say B. In order to do that, we use a mole ratio. So what we would do is we'd look at the balanced equation and say, hey, what's the ratio from the coefficients between A and B? Since A is what we're getting rid of, we would put moles of A on bottom. Since B is what we're changing to, we'd put moles of B on top. And then we would look at the numbers in the balanced equation, and we'd use that if it's a 3-to-2 or 2-to-3 or 1-to-2 ratio, something like that. We would use those in the equation. Once we get to moles of B, then our third step would be to convert from moles of B back to grams of B. And again, how do we do that? Well, we would have to determine 1 mole of B is a certain number of grams of B, and we would use that as a conversion factor. This little process below the diagram, this kind of tells you where you're starting. So we have what you have, A. We are typically going to focus for now on grams. I just tried to circle the G there. The L and the P. L would be related to liters if we were in gas, volume, and particles has to do with, number of atoms. We're going to pretty much focus on grams. And so what we would do, the first step of the process, again, follow the diagram. Step 1 right here is to convert from grams, because that's most likely what we'd have. Grams from the periodic table would go on bottom. Moles of A would go on top. So that would get us through step 1. Step 2, this second conversion factor here, has to do with the mole ratio. So what we would do is we'd use our balanced equation. We'd always put what you're getting rid of on bottom, what you're changing to on top, and then the numbers, number from equation, that would be the coefficients in front of B and A. So if this happened to be B on this side, if this was a 2 in front of B, and then on this side over here was maybe a 3 in front of A, well, then you would use this ratio of 2/3 from that balanced equation. Don't worry, I'll show you a sample problem here in a minute. And then third step is to get rid of those moles and change it to, again, we're probably going to focus for the most part on grams from the periodic table. So the mass of B would go on top. And as this would work out, grams of A would cancel, right? And then moles of A would cancel, and then moles of B would cancel. And then your final answer would give you, in this case, grams of B. So this is a 3-step problem. And this is sort of how the conversion factors would set up. I know I got a lot of drawing going on here. Don't worry, I'm going to work some sample problems with you, okay? All right. So let me move on to the next slide. Let me kind of show you how this works. So this first equation here, N2 reacts with 3H2 and 2NH3. We can use these coefficients in front, where it's kind of an understood 1 there, pretty much to mean that we have 1 mole of N2, 3 moles of H2, and it should make 2 moles of NH3, okay? And I went ahead and I put some numbers here. We're going to use 1 mole of N2 and 3 moles of H2, so we can have go with 3 sig figs. It says, how many grams of N2 would be used? Well, we are just dealing with 1 mole of N2, so all we have to do is get rid of moles and go to grams. This is just kind of to show you how this kind of all looks in terms of grams. So remember, N2, we look up on the periodic table, we do 2 times the mass of nitrogen. So 2 times 14.01, that would give us 28.02. So 1 mole of nitrogen would really be 28.0 grams of N2. okay? And then it says how many grams of H2 would be used based on 3 moles of H2. So if I take 3 moles of H2, I'm going to get rid of moles of H2 and I'm going to go to grams of H2. All we do is, again, look on the periodic table, 2 times 1.008. Hey, that's 2.016. That's the molar mass of hydrogen. So if I take 2.016 and I multiply it by 3 sig figs here, we're going to get 6.05 grams of H2, right? And then it says how many grams of NH3 would be produced. Well, if I have 2 moles of NH3 that's being produced, because that's what I would assume from the balanced equation there, then what I'm going to do is I'm going to multiply, get rid of moles of NH3, and I'm going to change it to grams of NH3. Again, a little bit of math out to the side here. Nitrogen is 14.01, and then 3 times 1.008. See what the calculator tells me, 14.01 plus 3 times 1.008. That gives me a total of 17.0, I'm just going to round it to 3 grams. If I take that and multiply it by 2, this turns into 34.07 if I went to the hundreds place, right? Technically with sig figs, it looks like I'd back it up 1. I'd go 34.1 because of sig figs here of NH3. So all I'm doing here is I'm trying to show you that we could also think in terms of grams, not just moles. So if you look closer here, it says, what does the mass of the reactants compare to the mass of the product? So if I add up the 2 reactants, 28.0 plus 6.05, that ends up giving me 34.1 grams of reactants, right? And if I look on the product side, based on my calculation, I should make 34.1 grams of NH3. Those should be equal to each other because the mass of the reactants should always add up to the mass of the products. So that's the law of conservation of mass or matter, okay? So this, I'm just trying to show you sort of how we could think in terms of grams instead of moles. All right, let me move on to some of the more, I would call practical problems, what you guys are going to see. All right, so given the same equation, it says how many moles of NH3 would be produced if 2.11 moles of H2 was reacted with excess N2. There's our excess N2, which basically means don't worry about N2. What we're going to do here, this is just a conversion problem. We are going to say, okay, so I have 2.11 moles of H2. That's how much I have to put in to this equation. What I want to do is I want to figure out how many moles of product can I make. In order to change from one substance to another, I have to think in terms of mole ratios. We're going to get rid of the moles we have, moles of H2. We're going to change it to moles of NH3 because that's what we're asked for. This right here is where we use our mole ratio. So what we do is we look back at our balanced equation and say, okay, what's the coefficient in front of H2? Hey, that's a 3. So I'm going to put 3 on the bottom next to moles of H2. And then next to NH3, hey, there's a 2 there. So that goes on top next to 2 moles of NH3. So now I have a conversion problem here so that my moles of H2 is actually going to go away. I basically need to multiply 2.11 times 2, then divide it by 3, and that's going to give me 1.41 moles of NH3. So based on the coefficients of the balanced equation, I can convert one substance to another. That's kind of what we're looking at there. Now, to get a little bit more complicated, let's talk in terms of grams. I have 9.47 grams of H2. I want to know how many grams of N2 would I need. So the process, again, is back to the diagram I showed you before. If I start with grams of one substance, I can't just go straight to grams of the other substance. what I'm going to have to do is convert to moles first. Then I can go moles to moles, and then I can go moles to grams. So here's how this is going to set up. Start with my 9.47 grams of H2. But we're going to get rid of those grams of H2, and we're going to go to moles of H2. And I'm going to map this out first, and then I'll come back and put numbers. So this first conversion factor is going to change me from grams to moles. Then I'm going to get rid of those moles, and I'm going to go to moles of N2. That's my other substance I care about here. But I don't want to stop with moles of N2, so then I have one more step. Get rid of those moles of N2, and I'm going to change to grams of N2, okay? Now, let's go back and fill in these three conversion factors. Anytime we are relating grams to moles, we're always going to put a 1 next to moles. So little calculation out to the side, I look up hydrogen on the periodic table, 1.008 times 2. That gives me the molar mass of hydrogen right there, 2.016. This middle step right here is all about looking at my balanced equation, just like we did before. Get rid of 3 moles of H2 from the balanced equation. And we put a 1, that's an understood 1 in front of it, N2. So notice our mole ratio here is a 1 to 3 instead of a 2 to 3 on this one, because we're dealing with nitrogen instead. That's our second step, the mole ratio. Third step, get rid of moles of N2. And then again, a little calculation out to the side, 2 times the mass of nitrogen, which is 14.01, gives me 28.02. Now, if you look closely here, things are going to cancel. My grams of H2 cancels. My moles of H2 can cancel. I've changed it to moles of N2. Now my moles of N2 cancels with my third step. And when I punch this into a calculator, anything on the top, I'm going to multiply. So 9.47. Anything on bottom, I'm going to divide. So I'm going to take 9.47 divided by 2.016. Get a number. Divide it by 3 because it's the same thing as multiplying by 1/3, right? And then I'm also going to multiply by 28.02. And that gives me my final answer of 43. Let me erase the decimal there. 43.9 is what I would round to, grams of N2. Okay. So that's how we would figure out how many grams of N2 would be needed. Now, how many grams of NH3 would be produced? There's really 2 ways to do this. If you think about law of conservation of mass, we could just add our 2 numbers, grams of hydrogen, grams of N2. That is one way to do it. But let me show you the other way to do it. The other way to do it is to treat this like a stoichiometry problem, which is what I'm going to do. I'm going to go back and say, okay, so I know I have 9.47 grams of H2. This time I'm going to get rid of grams of H2, go to moles of H2. So same first step. Don't recalculate, 2.016. The second step is going to be different here because I'm going to get rid of moles of H2, but now I'm going to change to moles of NH3. My ratio is a little different this time. You still put 3 on the bottom, but this time I put 2 on the top because this is a 2 to 3 ratio. And then the last step, since I'm going to grams, I need to get rid of moles of NH3. And then I need to go to grams of NH3. And that again is 14.01 plus 3 times 1.008, which gives me, I think we did it on a previous problem, 14.01 plus 3 times 1.008, 17.03. That's the molar mass of NH3. My grams of H2 are going to cancel. My moles of H2 cancel out. Moles of NH3 cancel out. Anything on top, multiply across. Anything on bottom, divide. So I'm going to do 9.47 divided by 2.016. Then I'm going to multiply by 2 and then divide it by 3 because that's that 2/3 in the middle. And then multiply by 17.03. And I get 53.3 grams of NH3 we would expect. Okay, again, way to double check that. Go back and say, well, it's 9.47 of one reactant plus 43.9 of the other. That adds up to 53.37. So there's some rounding in there that would change that to slightly different, but essentially it's the same thing, law of conservation of mass. All right, let me see if we got another slide here. I think we have one more to work with here. So let me go ahead and do one more problem with you. This equation right here, I'm going to move this down a little bit. Okay, this equation right here says what mass of water in grams is produced when the body oxidizes 1 gram of glucose. So start with our 1 grams of glucose, 1.00 grams of C6H12O6. What we are trying to figure out is the mass of water. So we're converting from glucose to water. So first step of the process, get rid of grams of C6H12O6. I'll spot you the molar mass here momentarily. We're going to change it to moles of C6H12O6. Second step, we're going to use the mole ratio. So get rid of moles of, I'm going to write glucose this time. We're going to change it to moles of water. Third step, get rid of moles of water. We're going to go to grams of water. Anytime you're dealing with molar mass, you're always going to put 1 next to moles. This middle step, that's all about the balanced equation. So if I look closely here, there's a 6 in front of water, so that goes on top. And there is really an understood 1 in front of glucose, so that goes 1 goes on the bottom there. As far as molar mass goes, let me run it up for you. We're going to do 12 times hydrogen, 1.008, plus I'm going to do 6 times carbon, 12.01, get an answer, plus we have 6 oxygen, so 6 times 16, get a total. The molar mass here is 180.02 is how I would call that. Okay. As far as molar mass of water goes, that's 18.02. We've done that quite a few times. 2 hydrogens, 1 oxygen. Now I punch this into a calculator. I'm going to do 1 gram divided by 180.02 times 6 times 18.02. That does not give me very much, does it? That gives me 0.601. Calculator says 0.60059, round to 0.601 grams of water. Okay. Next question, how many grams of oxygen are needed to oxidize 2 grams of glucose? Same kind of process. We're going from grams of one substance, but we're actually going to change to the other reactant. The problem is going to start out looking very similar. In fact, the first step is exactly the same. Get rid of the grams of glucose. We're going to change to moles of glucose. I'm just writing glucose this time instead of formula. Second step is to get rid of moles of glucose and go to moles of O2. This ratio, if you look closely in the periodic table, this is also a 6-to-1 ratio. So it looks very similar, although we're in a different substance. Last step of the process, get rid of moles of O2. And the molar mass, if you don't know it, is 32.00 grams of O2 per mole. Punch this into a calculator. 2 divided by 180.02 times 6 times 32.00. We're going 3 sig figs here, so 2.13 grams of O2 are needed. Okay. So that is definitely, I'm going to double check. Yeah, that looks right. That's the basics of stoichiometry. It's all about conversion problems. That's why we spent quite a bit of time in the first couple units or first unit of conversion problems doing this dimensional analysis, because you need to know how to do that for stoichiometry. So I would suggest make sure you get notes written down on this, and we will continue this the next time I see you. All right. Have a good one.